Welcome to the Water Circularity for CEA Facilities webinar. We're so excited about this. This is a presentation based on our best practices guide we just released this summer. More about that later. My name is Rob Eddy. I'm the resource efficiency horticulturalist. I always have to spit that out for Resource Innovation Institute. We're so glad you're here. Next slide, please. I'm going to do a little bit of introduction here. I think we've got an agenda. Is that coming up now? Oh, we'll do this poll alert first. Thank you, Bryce. Appreciate it. So we're going to do polls throughout the webinar, and we're just going to leave it up, and you can check it off whenever you get a second to. We're not going to wait for everyone to do it. So the first one is obvious. What kind of facility you're cultivating in? That helps us understand who we're talking to. So if you could fill that out, appreciate it. Next slide, please. Here's our agenda today. I'm going to give you a little introduction, a little bit of context. Then our subjects are economic rationale and water conservation practices, water disinfection and purification practices, getting to zero liquid discharge, water storage and biological remediation, which is something we've haven't talked about yet in any of our webinars. That biological remediation, it's remediation, and we're really excited about that, bringing that to you. And then we'll have Caleb Hayhoe come and talk about ICF incentives for energy savings. So you'll get a lot of applied knowledge today that you can take back to your facilities and start reducing your water usage right away, and also give you some ideas for incentives to cover some of the costs of future technology. We're recording today's session. If you have chat or questions, you can put it in our chat or comments, and we'll be happy to answer those at the end when we have a question and answer period. We'll also address some of those right away after each of us does a section of technical discussion. And this, I would say, I want to let everyone know, this is going to be a detailed presentation. We're going to get into the weeds a little bit with this one. So I just want to let you know ahead of time that there's a little bit of introductory, but then also a little bit of weedsy stuff that I think you'll enjoy. Next slide, please. Here's today's experts. We're going to introduce ourselves now. You've heard from me. My background is in greenhouse and growth room management. I was at Purdue University for 20 years, managing their plant growth facilities, for research facilities and teaching facilities. Prior to that, I worked for Dow AgriSciences and their world headquarters at their greenhouses as their horticulturalist. And since leaving Purdue about 6 years ago, I was a consultant for 5 years for the ag chem industry, the biotech industry, the vertical farming industry, and the cannabis industry. It was a lot of fun, but the sustainability stuff is what I really enjoyed, and that's why I jumped when I got a chance to come to RII. Jeff, are you ready to introduce yourself?
Jeff is still not here, so if we could skip to Carlos.
We'll do Jeff later. Carlos, go ahead.
Hey, everybody. I'm Carlos Salazar. I'm the Chief Executive Officer of Bear Ag and True Zero Corp. I am a liquid handling expert. I guess they call me that. I've been working in that for about 15, 20 years now. And we're here to talk about water conservation. So welcome, everybody.
Thank you, Carlos. Caleb, do you want to introduce yourself now or wait till towards the end?
I can just introduce myself really quickly. My name's Caleb. I'm the program manager managing the 2 ag energy efficiency programs for SoCalGas and Southern California Edison. And I'll go over some incentives towards the end.
Great. Thank you, Caleb. Jeff's having some technical stuff he's working out. We want to make sure it's perfect when he gets online. So we'll introduce him when he comes on. Next slide, please. The learning is not over after today. You can access our virtual classroom where you can get recordings of this presentation, plus other ones that we've done, some tip clips and other downloadable resources. Next slide, please. We've got upcoming workshops for SCE. This is the second of 4, and they just keep getting better and better. October 12th, be critical role of building envelopes. And October 26th, on commissioning CEA buildings and systems. So really important topics. And we're digging into the weeds of these topics. Next slide. We're really excited about two publications that have come out just this summer. the Best Practices Guide to Water Circularity, and the CEA Energy and Water Benchmarking Report. Both these have information that has never been released before. The Water Circularity one brings together the most recent academic research on water conservation and remediation, but also combines it with industry-informed content from our working group that we established from our members of RAI, which represented 25 different companies, fantastic working group. We also brought in some of the newest engineering discoveries as well, trying to bring those three fields together to write up these best practices guides for you. The benchmarking report has information on the resource efficiency of CEA facilities from utility bill level data, not just estimates, but this is the first time that that kind of data has been reported. And we really think it's an important read for you. Next slide, please. Here's an example of our benchmarking that we do at RAI. This is from our Power Score platform, where you can make an appointment with us, and it's free of charge, and you can bring us your utility bills, and we'll tell you what else you need to bring, and we'll provide you KPIs on your resource efficiency and your productivity, because both those things you want to track at the same time. So for example, energy consumption, water consumption, your water quality and production. So we highly recommend you get a hold of us. And Bryce, who is the wizard behind the curtain today, who's helping with this presentation, will guide you, set up an appointment and guide you through that benchmarking appointment. Next slide, please. Great. So let's look at our results from our poll, get a feel for who you are out there. It's a good mix. It looks like standard greenhouses have few more of those than folks growing in warehouses or small indoor buildings. And with NA being the largest group, so we've got a lot of people from various sectors of the industry, it sounds like. Great, thank you. Next slide, please. So this will be me presenting some information reducing water. Before that, let's do another poll so we can learn a little bit more. This is actually a knowledge check. This is kind of fun. I just like to know where people's baseline knowledge is. So answer this question sometime during my section. You don't have to do it now. About how much water that plants take up through their roots stays in the plant. Okay, so you can answer that anytime. Next slide, please. Great. So this is a Sankey diagram that shows the fate of water and CEA operations from two hypothetical facilities. One's a greenhouse and the other's an indoor farm. Now, the indoor farm doesn't recycle its HVAC condensate. We'll talk more about that later, but it's not the end all of technology. It's kind of a standard indoor farm, right? And the greenhouse is a standard greenhouse. So if you follow from left to right, you'll see the incoming water and then where it goes, the path that it goes, and what the final fate of it is. And this kind of gives you an idea. You may not have thought about this before. I know that I hadn't. It's kind of silly until I started writing this guide. The water, only 2% of it ends up in the plant at harvest. Most of it is lost to the atmosphere, either through transpiration through the plant pores or evaporation from the cooling pads that most greenhouses use, evaporative cooling pads. So most of it is just gone. And that's a problem. We really would like to recapture that if we could. And about 23% of it in a greenhouse becomes liquid waste of some form. Now, standard indoor farm doesn't have evaporative pads like greenhouses, right? So it ends up not needing as much water as a greenhouse in general. But there are other waste sources for indoor farms, particularly RO. RO is often used, reverse osmosis is often used to purify the water coming into the facility so that it's pure enough for hydroponics, okay? And RO, depending on how efficient it is, it can a lot of times it's wasting a lot of water. More on that later. Okay, but I just want you to see this and start thinking about where your water goes. What is the fate of that? Next slide, please. there's some good news with water use efficiency, and this is what we reported in the circularity guide, is that that claim that controlled indoor farms, controlled environment, and agriculture, high-tech facilities can reduce water by 90 to 95% over field production. That we've shown to be true in our guide and also in some of the academic studies that we found. Now, not everyone can do it. It takes you have to dedicate a lot of resources to it. But here's a great chart that shows the water use efficiency, that being the how much water in liters it takes to get a kilogram of harvested material, and starts with open field and goes all the way down. As it goes down, you get higher tech greenhouses, all the way down to you're at the closed greenhouse with advanced controls and CO2 and hydroponics. You're at that point where you're now getting a savings of over 90%. Next slide, please. You can achieve that fantastic goal of saving water, but what is the economic rationale for it? That's the big question. How can you justify spending the money on it? Well, one thing we found out from our industry working group was that the water savings aren't enough to justify it. And that's probably intuitive to all of you, that water just isn't that expensive. You can save, you can recirculate your irrigation water one way or another, and you can reduce consumption by 20 to 40%. But that's not going to pay for all that technology to recirculate it. But because CEA facilities fertilizer plants, by putting fertilizer in the irrigation water, that's where serious savings can come about. You can reduce your fertilizer costs by 40 to 50%. The fertilizer tends to cost a lot more than water, 3 to 4 times as much by the time it's dissolved in the solution that's applied to plants. And fertilizer prices have been really spiking recently. So this is where the opportunity is for money savings. CEA producers report a return on investment in as little as 2 years due to these fertilizer savings. Next slide, please. Given that's why when we suggest what is the highest priority, which types of water waste should you prioritize, we tend to lean towards wherever you've got fertilizer water that's being wasted or overused. Let's tackle that, because that's where you're going to get a lot of money savings. So the top two that we've indicated RAI for that prioritize for water waste is over irrigation and leaks. Those are things that anybody can do. Any facility can do that. Analyze their irrigation protocols. Develop a culture of conservation, so your folks have the tools they needed. They get the tools are close by to fix leaks. They get rewarded. You catch people doing the right thing and say, "That's great, thanks for fixing that leak." I mean, that is where anybody can start by reduce water. And then irrigation leachate, what comes out the bottom of the pot, so it comes out the bottom of the slabs, recycling that. And then there's others here. I won't go into them, but our expert panelists will. Next slide, please. So what are some of the ways that we reduce irrigation in hort substrate culture as opposed to hydroponics? I think most of these. Drip irrigation, incredible invention that's been with us for decades and has really resulted in reduced water consumption in the agriculture industry. There's also drip tape as opposed to drippers like you see on the far left, the drip tape in the middle. There are precision irrigation boom sprayers that move over the crop. There are ebb and flood benches, and at full-scale horticulture facilities, there are ebb and flood floors. So those are some of the ways. Next slide, please. If you invest in excellent climate controls that can be integrated into your irrigation system so that you're monitoring the environment, particularly if you're at a greenhouse, monitoring the environment, the sunlight, and also being able to activate those valves, then you can really start reducing the amount of waste that you use in irrigation. by doing it this way. You have layers of decision making that your programming is making. You're telling it you got a time clock function, so there's a certain times a day that you want it to be allowed to irrigate. Okay, you don't want to be watering at night typically. Probably want it to start a couple hours after the lights come on or the sunrise comes up, and stop a couple hours before sunset or the lights go off. So you got this window, and then within that window you want other things to tell it when to turn on. So it's allowed to come on in the window, and accumulated light, since the last irrigation, is one thing that can trigger irrigation, or the maximum interval, maximum amount of time, number of minutes since the last irrigation, which is sometimes helpful in low light in greenhouses, because sometimes you don't reach the accumulated light, but still you realize it needs to be watered. And then all that has to be adjusted for how big the plants are, how actively they're growing, what stage they're in. So crop aging factor. Now that's a lot of fancy lingo, but this is just what good managers do. A good manager knows from her experience that, yeah, I don't want to water at night. There's a window here, and a good manager in a greenhouse, she knows that, oh, we got a lot of sunny weather, we're going to be watering more frequently. I mean, all this is basically automating what a really good manager can do. Next slide, please. You can also reduce water waste by triggering irrigation with weight scales. This is very popular in the tomato, high wire tomato industry. The tomatoes growing up wires all the way to the rafters. Also strawberry production. You can see the weight scales here underneath that trough. You're not weighing the entire crop, just a certain section that represents the rest of the crop. Also, as you can see on the right, it allows the weight scales apparatus will have a drain sensor, so it can analyze how much water has come out compared to what you put in, and also the electrical conductivity, which tells you a little bit about the fertilizer status. Next slide. You can also, this is a one that I did for several years, and it was really fascinating work. You can use water content sensing. There are different kinds of moisture sensors, particularly the dielectric sensors that measure volumetric water content. Here on the bottom left, you can see a sensor stuck into a slab of stone wool. This allows you to trigger irrigation based on the obviously the substrate's level of dryness or wetness, and you can, with this tool, you can trigger irrigations like you see on this green line, which is kind of an idealized 24-hour period of how you should maintain your irrigation. It's much more technical than I ever thought it would be until I learned about tomato growers and how precise they are. The tomato industry has really revolutionized how to water because it's just so precise. It's really wonderful to see. So you can see the water it comes on and it reaches a saturation point, then it lets it dry out a little bit overnight, and then it starts off the whole series again. The blue line is the EC level, so you're tracking your fertilizer. Those both can be done with the same sensor. Next slide, please. Before I jump into this, I should also say that volumetric water content sensor, what I was using it for was research at Purdue University, and we were doing drought stress studies to see if we could increase secondary metabolites by applying controlled drought stress. Controlled drought stress means, we're being very careful about it. We don't want to reduce yield. We just want to increase the secondary metabolites, which could be the flavor compounds, the aroma compounds for food. It could be the active ingredient for medicinal crops. So it's a really cool technique. You can also, of course, reduce irrigation by using hydroponics, recirculating systems. I don't need to tell you all about these. I think you're familiar with most of them. There's, just as a reminder, nutrient film technique, which is used for spring greens and lettuce, deep water culture, raft culture, where the styrofoam trays are floating in a gigantic pond built inside a greenhouse or an indoor farm, aeroponics, and then, of course, the CEA industry has revolutionized hydroponics by the development of vertical NFT/aeroponics facilities. Next slide. Okay, all that good news I was talking about, I'm returning to the same chart that was the good news chart. There actually is bad news in it. This bottom row here, a greenhouse evaporative cooling. Notice that evaporative cooling negates all the it negates all of the benefit from the other technologies that you use to reduce your water consumption and therefore increase your water efficiency. And let's talk about that for a minute, because it's something doesn't get talked about because it's not sexy technology. Here's a beautiful, sexy picture of a brand new evaporative pad cooling system. All right, the water trickles down the pad because there's a reservoir, that black reservoir with a pump, and it trickles water down, and a louver opens behind it, and the fans come on the other side blowing out, so it's sucking in air from behind that pad. As air is drawn across the wet pad, evaporation occurs, cools the room. Oh, it just sounds great and it looks great, but let's look what it really ends up looking like. Next slide, please. Apparently, I'm the only one who takes pictures of what evaporative pads look like 2 years later. Of course, it depends on the quality of the pad and the quality of your culture of your employees. But this is what they often look like. They're leaking like heck. Some of those leaks cause algae slicks on the floor, which are dangerous. The evaporative pads can actually get biofilm, scale, algae growing on them. And in this case, and this is me, this is one of my greenhouses, so I'm not putting anyone down, cottonwood seeds that were floating in the air, and they were sucked in and landed on the back of that pad, then it got calcified, so it cut down on the effectiveness of the pads. The empty reservoir you see here is a pretty scary place to work. It's slimy, you're down on your knees in cement, and it's not very glamorous work. But because of that, if you don't adjust these pads for their flow rate and then the bleed off rate, which you're trying to bleed a little bit of that water off all the time, otherwise it concentrates with minerals due to the evaporation. If you don't adjust those well and do that unglamorous work, you could be wasting for a greenhouse, an acre greenhouse, you could be wasting millions of gallons of water a summer, a cooling season. I know. Okay. Next slide, please. Okay, let's talk about our knowledge check. Wrapping up here. Oh, excellent. Excellent. The correct answer is 2%. Most of you got that, so I'm glad you know that. You're better than I was. I didn't really realize that. I've been a horticulturist for 35 years, and I didn't really have a grasp of that until about 10 years ago. So good job there. Next slide. Okay, we're going to wrap up my part, and I'm going to ask a poll question next, and then we're going to have Jeff Martens come on and introduce himself briefly, and then he's going to jump into his presentation on water quality. So next slide, please. So here's our next poll. How do you measure water usage? You can check all that apply. Maybe you don't do anything. You've got no metering. Maybe you've got 1 meter, or maybe you've got more than 1 meter. We're really interested in knowing this. Or maybe you only track it using your irrigation control or your climate control computer. So I'll leave that up there. Jeff Martens, feel free to introduce yourself and launch into your presentation.
Thank you, Rob. Can you hear me okay?
Yeah, you're great.
Okay. Well, my name's Jeff Martens, and I've been in the water industry for 30 years. In most cases, I've been developing technology for disinfection, filtration, and water reuse. And in the last 5 years, I've been working on those technologies for the indoor agriculture marketplace. And I'm currently the VP of Business Development for Nuterra. And what I want to talk about today is water quality to begin with. What does the water quality look like, and how can you tell if it's good enough water to use directly or if it needs to be treated? If it does need to be treated, how will reverse osmosis impact your operations? And then we'll get into some filtration and disinfection technologies and wrap it up with some design considerations. Next slide. If you haven't had a chance yet to look at the water quality best practice guide. I'd highly recommend it. This table here that you'll find is table 1 in the guide. I think it's around page 11. And you'll see here the different components that the ions that you'll find in water and what are the desired levels for high quality irrigation water. So this is the table, and then you ask yourself, well, what does my water quality look like? And I want to point out also that there's a tool at www.cleanwater3.org, and that tool is very useful. You just plug in your water quality and it'll give you what the implications are and how to correct against that water quality. So let's take a look at the next slide. And this is well water results from a well that we tested in our area in the central coast of California. And you'll see highlighted in red are all of the water ions that are well above the recommended guidelines for good irrigation water. So this is not uncommon in California, where if you just take pure well water, that water quality is not good enough to use directly for irrigation. And if you're going to recirculate or reuse any of the water, then these things will concentrate up and it'll become actually even worse as an irrigation water. So you can see things like higher pH, high alkalinity, high nitrates, high sulfates, high conductivity. You'll find these in California well water. Next slide. So this is that Clean Water 3 tool that I talked about. And what I've done is I've just taken some of these constituents from this well water and put it into this tool. And if you'll go to the next slide, you'll see that this is the printout from the tool. And it'll say, well, the pH is higher than recommended. The alkalinity is higher than recommended. And what you'll need to do to improve this is add acid to the water before you begin irrigation. Now, a lot of the nutrients are acidic, and that'll bring your pH down, but you may need to add acid as well, just to maintain that lower level of alkalinity. If not, that alkalinity will build up in your soils, and at the root level, you may have a localized, even higher pH concentration because of the buildup of that alkalinity, and that will impact your nutrient uptake and your plant health. Next slide, please. So here, for anyone that's using municipal water, I have an example of Los Angeles City municipal water. And you can see that this water is not that much better. Still a lot of very high concentrations. You'll see a lot of red here for these different ions. The alkalinity has reduced a little bit, but chloride level is higher, most likely because they're adding bleach or chlorine to the water to disinfect it for drinking water. And that's also a component that you'll want to take out of the water before irrigating your plants, and certainly if you're going to cycle it up. Just an example here again from the best practice guide, table 7 just describes for you the high pH, alkalinity, and hardness, where it comes from water flowing through limestone and bedrock before it comes to your facility. And then again, what the implications are and how to treat it. Next slide, please. This chart, I've added a third column here as an example from irrigation runoff and the water quality of that irrigation runoff. And you'll see there's much higher level of nitrate, calcium, iron, potassium, and that comes from the nutrients that are added to the water. And these are much higher levels for fertigation purposes, and it's expensive nutrients. So if you can reuse this irrigation water, keep those nutrients in there, it'll be less expensive, and it'll eliminate you or minimize how much would be discharged either back to the municipality or to the environment. In one case, it can be costly, and in another case, it can be bad for the environment. So reusing this nutrient water can be beneficial, but it takes some filtration and disinfection. Next slide, please. I've added a fourth column here, and this is the water quality that you'll get from your condensate if you recapture condensate from the farm. And you can see there's nothing red in this condensate column. The water quality is very good, and it can be used directly in your irrigation process, or it can be used to dilute your incoming water and reduce some of the bad ions in that conductivity water, or in that makeup water. So if you can reuse your condensate water, it's a good, clean source of water, and an excellent source to minimize the impact of these ions and high hardness. Next slide, please. So this is the start of what we're going to talk about just in terms of the water scheme for bringing water into your farm. And so in California, with this bad water, we'll commonly take that incoming water. If it's municipal, we'll probably run it through a carbon filter to take out the chlorine, and then we'll send it to a reverse osmosis system that'll take out 95 to 99% of all of those constituents. And that water is stored here in what we'll call the clean water storage tank. And then you can send that off to the farm, add fertilizer, and do your irrigation. Next slide. We've talked about multiple sources of reuse and multiple sources of water. I'm going to focus on the two here that I've talked about already, and that's the condensate water that can be captured and reused, and the irrigation runoff. And the common configuration is to capture that condensate in a sump and then pump it over and collect it into another clean water tank. You can bring it right back to the main clean water tank, but there are some benefits to having a separate condensate clean water tank that I'll talk about a little bit later. And then the other source is the irrigation runoff. Again, it goes to a sump, and you can pump it to a storage tank that is commonly called a dirty water storage tank, or irrigation tank, or drain tank. And that should not be added to either the condensate tank or the clean water tank, because with it, you're going to have some bacteria loading, some possible pathogens. You have all the fertilizer, and you want to be able to control when you're going to reuse that irrigation water, and then also be able to control. Oftentimes, you'll want just pure clean water, and if you mix the irrigation water in that clean tank, you won't have any pure clean water source. Next slide. So let's now talk about filtration and disinfection. And I put them here together because they are closely tied. I'll talk a little bit about testing and technologies and particle size analysis, and then the impact on disinfection. Next slide. So this is a particle size analysis that you can run on a sample of your irrigation water. And this will give you an idea of how many particles do you have, what is the size of the particles, and what is the volume and weight percent of those particles. And that helps you design a proper filtration system. You can see here there are many small particles up at the top, from 1 to 5 micron in size. And then you'll see there's another blip somewhere around the 15 to 40 micron size particle. And it doesn't look like there's many, but if you look at the table on the bottom, it's a little bit cut off, but there's a high volume percent and a high weight percent from those larger particles. And if you don't design a coarse filtration to take care of those, they'll foul your fine filtration filter, and you'll spend a lot of time cleaning that filter. Next slide. So why is it important to filter all of these particles? And the answer is because this algae, plant material, soils that are the particulate, they create a great environment for bacteria and pathogens to begin to grow in a protected environment. They have a little microenvironment where they create a good area to grow. It's hard to get disinfectant in there. The pH may be localized, and that slows the flow down. So it really creates a nice environment. And you won't notice it right away, but after a period of time, all of a sudden, you'll go from having a clean water environment. You may have an outbreak of pathogens or an outbreak of bacteria that create a big fouling scenario, and your plant yield will begin to deteriorate. The fouling increases, and this is a little cycle that builds upon itself until it gets to a point where you'll have to mechanically clean your irrigation lines. Next slide. This is an example of how bacteria grow on a surface. And there's one important point I want to make from this. And you can see that the bacteria start on the surface, they adhere to the surface, and then they start to excrete this slime layer. And the slime layer protects the bacteria from disinfectant and water flow, and creates a really nice environment, again, for the bacteria to rapidly increase, again, creating more slime and fouling. That slime will collect some of the particulate that's passing through and create just a fouling scenario. And the thing I want to point out is these bacteria will stay adhered at the location where they start to form. The bacteria don't release and circulate through your entire irrigation system. So you need to have a disinfection plan that'll reach out and get to all of the areas in your irrigation lines. If you have a disinfection system that is protecting in just one area, it may not reach out and protect from bacteria growth across your irrigation line system. Next slide, please. We'd like ozone, and many farms have asked for ozone. There's some advantages to that. It's the strongest oxidant that you can have, so it's very effective. It doesn't build up a residual. It has a half-life, so just over time, it'll start to degrade into water. And it will also increase the oxygen levels in the water while it disinfects. It's not the best a disinfectant for all scenarios, which is why if we move to the next slide, you'll see we have a table in the best practice guide that lists many of the disinfection technologies, some notes about them, what their effective treatment ranges and advantages and disadvantages of those various technologies. And honestly, the best approach is to use multiple disinfection technologies. I know it adds a level of cost, but really using 2 or sometimes 3 different technologies for different purposes is the most effective strategy. Okay, next slide. Okay, this is the last slide that I'll talk about. And you see I've added to the diagram here where we would recommend adding filtration and the disinfection in this schematic. So if you look at the condensate return line from the sump, you'll have a pump probably at the bottom of the sump. And then you may want to take that condensate and run it through a small ion exchange resin bed, because condensate can often pick up heavy metals from the HVAC equipment or the building structure itself. And depending on your crop, they could build up to a level that could be could harm the growth of the crop. And I know in the cannabis industry, they can't have any metal ions, added into the system, because that'll make their finished product non-sellable. So often there'll be ion exchange. It's pretty easy and not very expensive to add to that. And then it'll go to that clean water storage tank. On the irrigation side, again, you'll have a little bit larger pump that's strong enough to pump it through what either a media filter or a rotary screen filter. And that filter there will remove the larger particles so that they don't build up in the water and cause problems later. And that's stored in the dirty water storage tank. Now, down at the left-hand side, this is a schematic for an ozone filtration system. And we'll just recirculate the waters from both the dirty water tank and the clean water tank through this ozone generator. And that'll distribute ozone into those tanks and maintain an ORP level, an ozone concentration, to keep those tanks disinfected so that high levels of bacteria and pathogens don't build up in those tanks. And often you can design an ozone system, if those tanks are close to one another, that can take care of both tanks. It's important to note that the condensate, because it's relatively clean, is easier to treat with the lower level of ozone, and the dirty water storage tank usually requires a higher concentration of ozone to keep it disinfected. So thank you, Rob. That's the end of my talk at the moment.
Rob, you're muted.
Thanks, Jeff. The schematics were wonderful. So I think the audience can tell that there is these are topics that you'll need water treatment experts with horticulture facility background, of course, because it's like you would if you're buying HVAC or lighting. You need to have experts that you can talk to. The best practice guide, what it's great for is kind of as a primer, so you can have that. It's a free download, and that will familiarize you with the terminology and the different systems. We haven't even talked about all the systems yet. So the combination of those two would be really effective for your planning. Okay, and with water treatment, I think both of our experts would tell you, it really has to be there. The water treatment, you need to be planning for that as you're designing your facility, because it just takes a lot of input, a lot of good ideas. All right. Jeff, a real quick question. The bacteria you're talking about, I know it's often referred to as biofilm. Let's emphasize that. Do you mind telling us again about what happens if you don't control biofilm?
Yeah, so the bacteria, as they grow, they excrete this biofilm, and the biofilm is sticky. And then the particulate that is floating through the soil, the algae, the leaves, some other particulates from your plant growing operations will start to accumulate rapidly in that biofilm. And then the bacteria have even a greater environment to grow in. So they just multiply upon themselves to where your irrigation lines will foul up and plug, or get the water flow is so low that you have to go in and flush them out in a mechanical cleaning step.
Thank you. And the biofilm also, it can host plant diseases. It just turns into this quagmire of bacteria and other things going on, and it's hard to control because it protects itself. It forms like a scale on your pipes, and it's hard to get anything to get in there and disinfect it. So
yeah, that's right. That pathogen We'll find any pathogen that you may have, a mold or yeast that you're concerned about, will love that environment, harbor itself in there, and make it even more difficult to treat against that pathogen.
Yeah, and this is relatively new stuff. I mean, most of us who work in the greenhouse have seen biofilm and pipes, or you can feel any sort of container that you keep stagnant water in. If you just go a week later and rub your hand in it, you can begin to feel a slimy coating. That's the beginning of biofilm. This is a relatively new science of learning about just how insidious biofilm can be, right? There's a whole biofilm institute at, I believe, Kansas State that we've referred to in the guide for information. And it will form everywhere. You're not going to be able to avoid thinking about biofilm. In fact, and I'll just have Jeff confirm this statement, I think one of the recommendations that I now make to people is when you're deciding what kind of disinfection you're doing, start with what's going to control the biofilm. And then that might dictate you'll need at least one technology that takes care of that as good as you can. Then you may need some others, but kind of prioritize that. Jeff, is that sort of thing you talk to your customers about?
Yeah, absolutely. That's right. You have to have a method to keep the biofilm under control. Otherwise, it'll just be a matter of time until you have a fouling issue.
Yeah, and so when you talk to these water experts, there'll be some solutions they have for you. Jeff mentioned this, that are they're point control. They control right then and there, like UV light. Great system, works really well, but there's no residual. It doesn't go downstream and kill anything. So you can't rely on just a point treatment. You've got to have a combination of point treatments and then something with a residual treatment. There's several things that are controlled biofilm, ozone being one of them. Okay, let's look at the results of our poll. And thank you again, Jeff. That was wonderful. So we have this is great information. This really helps us out. So thanks for answering this. We have kind of a tie, 1 meter or more than 1 meter is how people are getting their information on their water consumption. They also track it with the irrigation controller. I just want to remind people that's one way to do it. So don't forget that you probably, in the programming there, it probably is a piece of data that you might not remember is there. And climate control computers, of course. All right. Next slide, please. Oh, this is going to be fun. We're going to have Carlos speak about zero liquid discharge. This is really taking it to the level which you may think is, I don't want to use the extreme. This is like really taking it all the way, try to limit, not just reduce it, but try to take it down to zero. This is what's happening in Europe right now. This is what the Netherlands is mandating for their operations by 2027. So it's serious stuff. Before we get to it, let's do another poll or knowledge check. Filtration can improve the efficiency of many other water treatments. True or false? Answer that at your leisure. And now I'm going to turn it over to Carlos Salazar.
All right. So let's have a little bit of fun with ZLD, or otherwise known as zero liquid discharge. We're going to be covering everything zero liquid discharge, what it is, the history behind ZLD, how it works, why it is required or it will be required in the future, and why it's necessary. We will also discuss the technologies required to achieve ZLD and, pitfalls and that sort of thing. Next slide, please. So what is zero liquid discharge? Let's first start with the fact that water is at the core of the sustainable development that is occurring in the world right now. Moreover, it is essential for social, economic, and environmental well-being. However, water resource availability has been significantly threatened in this last century or so. Next slide, please. To overcome this problem, we've made up developed desalination, and it's a robust and mature technique for obtaining fresh water from salt water, and is considered an efficient and reliable process. However, there's growing concern about the adverse environmental impacts generated by the brine, where the concentrated rejection by desalination results in high salinity together with chemical residues. So we're putting a lot of high salinity water back into our waterways. Zero liquid discharge is the engineering approach to the recycling and the treatment process of water to prevent the discharge of liquid effluent into sewers, surface water, and other water bodies. The end product of a ZLD system is a solid salt waste that must be disposed. It's usually through a landfill. This water can be used indefinitely in a closed loop. Next slide. So traditionally, ZLD systems include the use of evaporators and brine crystallizers to separate salts from the water. The evaporation systems used in ZLD for water recycling consist of brine concentrators in the form of evaporation systems and brine crystallizers. So what this does is essentially separates the water from the actual salt crystals. Next slide. And we'll get into that here in a little bit. So the history of zero liquid discharge. It was developed in the United States about 50 years ago for the power industry, according to the EPA. The largest developers and users of this technology around the world are the United States, India, and China. The increased salinity of the Colorado River is what led to the regulatory mandate of ZLD and for all the nearby power plants around the Colorado River. According to the EPA, the majority of GLD systems operating within the power industry treat blowdown water from cooling towers and boilers, many of them recycling over 99% of the blowdown water back into the cooling tower. Additionally, with increased freshwater pollution and salinity, there's been an uptake in ZLD adoption in the electronics, fertilizer, mining, and chemical industries. Next slide, please. So why is ZLD required and necessary? In general, freshwater supplies are being depleted by natural and anthropogenic activities, such as rapid population growth, industrialization, and intense agriculture. In addition, one of the main causes of water resource shortages is water body contamination. Nitrate pollution is considered one of the most pressing global environmental problems, both in surface and groundwater. As national clean water reserves become depleted and wastewater treatment facilities are increasingly overtaxed with industrial runoff, ZLD systems are becoming an important consideration for many companies, municipalities, and regulatory agencies. ZLD systems are essentially facility water management systems which reuse and recycle 100% of water waste, such that the only waste leaving the facility are in concentrated form, as we just discussed about previously. ZLD systems have the combined benefit of significantly reducing facility freshwater usage, completely eliminating sewer discharges, and substantially reducing the volume of waste leaving the facility. Oftentimes, over 95% of the volume of liquid waste leaving a facility is water. It is water. If this water can be purified and recycled on site, the benefits are immeasurable. As water scarcity intensifies globally, the capability of ZLD for wastewater recovery to the largest extent further enhances its prospects. Additionally, increased public environmental awareness is an additional driving force, since ZLD avoids the negative environmental impact of wastewater discharge, reducing the public concerns. Now, this is where it gets interesting, guys, and I'm sure a lot of you know this, but the CEA market is expected to increase by an annual compound growth rate of 18.13%, growing from $74.2 billion in 2022 to an expected $377.6 billion by 2032, according to market.us. So we can expect upcoming regulation to reduce and/or eliminate wastewater from these facilities. There are many cities with laws already in place that prevent the discharge of effluent with fertilizers and pesticides, and we expect this number to grow exponentially in the coming years. With this looming change in the horizon, it really makes sense to invest for ZLD, as there are and will be incentive programs to help transition CEA facilities to ZLD. Additionally, the regulation of wastewater is already preventing some CEA facilities from obtaining permitting, severely limiting their operations or preventing them from operating altogether. When you think about it that way, ZLD becomes critical to the existence of some of these facilities. With the deployment of ZLD systems, there's also an opportunity for CEA facilities to market themselves as socially responsible enterprises and benefit from marketing, something that's not really very common in agricultural practices. Next slide, please. So how do we achieve ZLD? So it is a multi-technological process, sometimes achieved as a phased process, meaning that we have to do it in phases. New CEA facilities in the design stage have an advantage over existing ones, specifically in regards to infrastructure development. Since ZLD is a multi-technological process, it requires a significantly larger footprint than traditional water treatment systems. This can include holding tanks and multiple skids that can handle various water types. ZLD can still be achieved with existing facilities, but it requires proper engineering and design to ensure minimum impact to the existing operations, as nobody wants to, build infrastructure with plants in the building. For both new and existing facilities, a successful phased approach can be achieved if it's planned correctly. Sometimes the financial upfront commitment of ZLD discourages potential implementation. However, with a phased approach, it can be way more palatable. In order to achieve ZLD, the water system design must be such that it creates a minimal wastewater discharge first, meaning we have to reduce, most of our waste as much as we can. In a CEA facility, this means that we have to recover our primary RO reject, runoff recovery, and condensate recovery at least. And both Rob and Jeff have spoken as to why recycling runoff and condensate is important. So I'm not going to get into the weeds on that, but I'm just going to talk about the process a little bit more. So reverse osmosis concentrate streams are further concentrated to create a sludge. Normally, RO concentrate is just dumped on the drain. In a ZLD environment, that's not the case. We recover it all. Plant water runoff is typically filtered through multiple filtration systems, including an RO membrane system with special high-fouling membranes that require clean-in-place systems to keep the membranes renewed and working in tip-top shape. Evapotranspiration is essentially distilled water. So condensate is like, as Jeff mentioned, is very, very clean water. And, we need to reuse that as much as we can because it's the cheapest water we can get, frankly. However, this water can still have some bacteria and some metals. Usually 100% of this water can be recovered, though, with no loss. Next slide, please. So, full zero wastewater discharge has proven challenging in the past due to the final step, which is solids concentration and removal. As a concentrated brine is introduced into an evaporator, the liquid water is released from dissolved solids in the form of steam and allows the previously suspended solids to fall out of suspension in the crystallizer. This crystallizer collects the solid salts, which will later need to be removed and disposed of. So in the picture screen that you see where you see the concentrated brine holding tank feeding the flash evaporator, and then off the top of the evaporator we have a stream system which is then condensed and turned into water again. At the bottom, you would have your solids removal. Next slide, please. So how do you turn the sludge that is left over into an actual solid so that you remove all the water? There's many ways of doing it. However, today we're going to speak specifically to MVR. MVR is probably one of the most common ways and best technological ways of achieving it. So let's get into the weeds a little bit as to how it works. It can be achieved, like I said, it can be achieved in a matter of ways, but MVR is the most energy efficient method. So that's actually a lie. The most efficient method, as far as the cheapest method, is passive evaporation ponds, but that's just evaporating the water into the atmosphere. And so we don't want to do that. So MVR is also known as MVC and is mechanical vapor recompression or mechanical vapor compression. They're just simply heat pumps. Their thermodynamic cycles are very similar to refrigeration cycles found in conventional home heat pumps and central air conditioning. The difference is that the working fluid inside of it is water instead of refrigerant like Freon. So the principle is the same, however. A compressor pressurizes the steam across a heat exchanger against an expansion valve. The steam condenses into water, giving up its thermal energy to a cooler feed water stream on the other side of the heat exchanger. The feed water evaporates into the steam and enters a compressor where it is recompressed and made available to reheat additional feed water. The excess condensate is drawn off as purified distilled water. All the energy that is put into the system is via the compressor. There are no heating elements or gas-fired boilers. Additionally, the compressor can also double as a vacuum pump, which puts the whole system under vacuum to lower the boiling point of the water and therefore the overall temperature of the system. which again further increases its efficiency. MVR systems are substantially less energy intensive than conventional evaporation systems, which is why they're becoming more and more common, with some of them boasting greater than 90% energy reduction over systems employing electrical resistance heating elements. Next slide, please. So out of the MVR, we still might get some wet salt material, which then has to then be further dried. So this is the final stage of a ZLD system. On the screen right here, you have a decanter centrifuge and a hydrocycle. We're not going to really get into the technologies as to how they each individually work, but we're going to talk about, in general, what's needed. So the solids removal that we must account for. In the past, there was these brine crystallizers that were commonly employed as forced circulation crystallizers to concentrate the brine blowdown from upstream concentration equipment. The solids byproduct gives the option of recovering the salts at the end of the ZLD process. The drawback to using crystallizers, as they have been used in the past, is the takedown of the equipment for cleaning and the maintenance processes, as the crystallizers tend to cake up the salts, making the physical removal of salts a chore or create the need to include scrapers and other mechanical equipment to physically remove salts from inside a crystallizer. However, there are novel ways of dealing with salts, such as the use of oil as a transport medium at the time of evaporation, which prevents the salts from fouling up the equipment and it prevents it from adhering to other surfaces. This oil then transports these precipitated salts as they are no longer in suspension, as salts have a much lower solubility level in oil. A decanter centrifuge or hydrocyclone, which I mentioned, they're both on the screen, typically separates up to 99.9% of the water from solids. The remaining water is just recycled again as distilled water and put back into the recycle loop where the MVR can use it again. The solids, they just need to be disposed of as solid waste, typically in a landfill. Most landfills in America accept this type of solid waste. Next slide, please. So this is a general diagram of a ZLD system in a CEA facility. In this case, the ZLD consists of a first stage RO for water treatment and purification of the source water, a second stage RO for the concentration of the facility brine water waste, as well as the concentrate water from the first RO system. A distillation system using a novel biphasic direct contact evaporation system to distill the concentrate from the second RO state, and an HVAC condensate recovery system. Again, condensate recovery is always going to be the cheapest water you can get. We highly, highly recommend that you recycle condensate if you can. Next slide, please. So not everything is rosy with ZLD systems. There are some reasons, and there are reasons why people don't employ them more. Although they do hold great promise to reduce water pollution and augment water supply, its viability is determined by a balance among the benefits associated with ZLD. So energy consumption and capital operational costs are a big deal. Therefore, it is imperative to understand the drivers and benefits that make ZLD a realistic option for you. The most noteworthy drawbacks to the ZLD systems are increased in both capital and operational maintenance costs, diligence, the difference in the design of ZLD systems compared to other water treatment systems, complications of dealing with complex streams of the wastewater, increased usage of chemicals such as sulfuric acid in the treatment of wastewater, intensive consumption of energy, which they are, and obviously the large amount of solid waste that is generated that must be disposed of. And that is the end of my presentation. If anybody has any questions, please let us know in the Q&A and we'll be happy to answer them.
Great. Thank you, Carlos. Really appreciate that on so many levels. It's great that you're willing to talk about the disadvantages too. This is what's so great about industry working groups for REI. They take off their company hat, kind of put on the industry hat to help us all out. I appreciate that. And Carlos, I learned so much here. And one, I did not realize that ZLD the first slide, was developed in America for power plants to keep from contaminating the Colorado River. That's new information to me. Thank you.
Yeah, absolutely, no problem.
I'm embarrassed. I could have put that in the best practices guide, but I never asked that question. I always assumed it was a European invention. And this isn't a question for you. I couldn't help but think, when it comes to the consumer's preferences, I hope that there's some research going on now by economists looking at, would consumers be willing to pay more for products that were grown with a ZLD label? Because ZLD, it's so easy to understand. It's kind of like organic label, even that's got a little bit of cloudiness to it, but it's so easy to understand. And then that would, more would help offset some of the additional costs to it. The one question that did come along was, can you tell us a little, I appreciate you talked about that, it's very energy consuming. Can you tell us any more about that? One of the questions from Evan was what is the typical energy profile for a ZLD system?
Yeah, so that's a great question. It's, to be honest, the answer is highly subjective. The biggest consumption of energy in a ZLD system by far is by the evaporation system. So literally the amount of runoff recovery directly affects the cost to evaporate water. And so our conversation with clients and CEA facilities is always around, what is your runoff percentage? Because if you have a 10% runoff versus 20% runoff is literally double your energy cost. It's really that simple. And so because the way that these systems work, they're very, very energy intensive. It takes a known amount of BTUs, and I can't recall off the top of my head what it is, but it's a known amount of BTUs per gallon of water to evaporate. That's just, it is what it is. There's no other way around that. And so in order for us to distill, and really the only way to separate the salts from water is via distillation. And so the best way. And so it's a I don't have a good answer for you, because it depends on the size of the facility. It depends on the size of the runoff, but it can be very, very expensive. Some of the designs that we have and some of the systems that we've implemented, an evaporator can spend up to $50,000 a year in natural gas versus about $20,000 in electricity. And we are talking about evaporating 2,500 gallons of water per day.
Right.
So
I appreciate that. That's really fascinating point about it. One of the big factors is how much runoff do you have? So I know it's a hard thing to answer, but that's an excellent point. It kind of goes back to what I keep rediscovering through this process of learning more about water circularity, that so much is dependent. It's like water quality determines consumption. That if you can start off with really excellent water quality, then you don't need to have as much runoff or over application to leach out your salts. Same thing with hydroponics. If you start with really clean water, you don't have to. You can recycle it more for a longer period before it becomes fouled with maybe too much sodium. So then it points back to the circular reasoning of, one way to get high quality water to start with is by collecting these nearly pure sources of water, such as HVAC condensate. And if you have rainfall, of course, that's wonderful too. But we know that's not true everywhere. So great answer. Appreciated that a lot.
You actually brought up a really good point too, because one thing that is, and you mentioned it earlier in your slides, when you have evaporation up to 75%, that's 75% of the water that was fed to that plant. So if you're able to recapture, even 90% of that, you're subsidizing essentially 50% of your water treatment.
Yeah, and you're really closing the loop when you're capturing so much water, like 90% of the water you're applying for irrigation is just going right out the pores, and typically just going right out your vents and into the atmosphere where you can't practically use it again. It'll rain somewhere, but not probably where we need it. So it's just, yeah, excellent point. Hey, we'll keep moving on. Next slide, please. Great job, Carlos. Okay, knowledge check. Everyone got that right. Well done. Next slide, please. Okay, I'm going to talk a little bit, just one slide on storage, just a couple of points about storage, and then we'll talk about bioremediation, which will be fun because bioremediation wouldn't get you to zero liquid discharge because, well, I'll hedge on that a little bit because it's usually done outdoors. And so you're letting the liquid get outdoors. So you're not zero liquid strictly defining it. But it is another way to treat water that's left the facility so that it doesn't go into the sanitary sewer, doesn't go into a local body of water, you know, so it'll be a fascinating subject to kind of compare and contrast. All right, we're just asking if you've downloaded an RII best practices guide before. Yes, no, or chances are you've downloaded a lot of stuff you just can't remember. So if you can answer that at your leisure, and we will move on. Next slide, please. So a couple tips about storing water for reuse. Again, you'll need advice from water treatment experts, horticultural water treatment experts. But two things I want to say is it takes a lot of room. It's a lot of, you can do it outside, you can do it inside. The outdoors does kind of depend on your region, of course, because if it's really cold, you're going to have freezing, or at least the water is going to be really cold. So you're going to want to temper it or let it reach room temperature before applying it to plants. But you just need to plan for a lot of space. And sometimes this is hard because you'd rather be growing plants with that space. The second point would be water that's being stored should never be allowed to be stagnant. Even if it's clean, even if you've cleaned it up, you still want to recirculate that, having it run through some point source like a UV disinfection loop, which we have a photograph here on the right. So two things, lots of room and don't let it go stagnant. Next slide. So here's a list of biological water quality treatment systems, and we've got tables like this in the best practices guide for, you know, physical or chemical, but this is biological. I want you to look under the green horizontal bar treatment range. What's exciting to me that I didn't know, that's why I wanted to do a whole chapter on this, is what it will treat. Pathogens. Biological water treatment can reduce nitrogen and phosphorus, and look at that. Even some agrochemicals can be treated with these means. Now let's go into what we're talking about. Next slide, please, Bryce. Bryce Carlton is advancing the slides for me, and he's the one who wrote this chapter in the best practices guide. So he's the expert. I'm just kind of puppeting what he wrote. First, we'll talk about constructed wetlands. I just want to point out that these tend to need a lot of land. So indoor farms may not have land, but greenhouses tend to have it. So just some slides to give you an idea of how large that is. And then the overhead aerial view on the photograph on the right of Monrovia Nursery can kind of show you that red box is where their constructed wetland is. Let's keep talking about it though, other than size. Bryce? Can you move the slide? There can be surface flow constructed wetlands or subsurface flow. Obviously, the surface flow the water remains on top, kind of like looking at a wetland. You know, you see the water on top, and in subsurface you don't. Look at these removal efficiencies. Look at what these things can do. They can reduce nitrogen by up to 99%, phosphorus by up to 98%, pesticides 97, and even the heavy metals that might be accumulated from your HVAC, from the plumbing and stuff like copper, zinc, and then even some toxic chemicals like lead and cadmium and aluminum and manganese. So relative to other water treatment technologies, these are high removal rates. So it's really cool. And there's a lot of science that's been devoted to this too. So it's not just hype. And we can help you in our guide, provide you information for getting more sources. Next slide. Slow sand filters, where the water is allowed to filtrate through a sand bed. What ends up happening, the sand bed on its own forms this kind of layer of different kinds of organisms. It's got a special name, which I can't pronounce, but it's like algae and bacteria and such, which actually help tie up some of the contaminants. It's not just filtering. There's a whole symbiotic system going on of removing contaminants. Now, what's cool about this is it can be done outdoors. It also has the ability to be done in containers, like you see these red ones here. That means it could be done inside. So this might be a solution for indoor farms to have a biological remediation system without having to have it outside. The other picture is them installing a slow sand filter in what's essentially a septic tank. It's they just reused that, and not reused it, but they're using the concrete bunker from a septic tank. Next slide, please. Also, biological remediation can be floating wetlands that you can construct yourself. And there's companies that have specialized in what the plants you use and the kind of rafts you use to float this on a pond. The neat thing about this is it can be retrofitted to existing holding ponds, which many greenhouses, particularly the floriculture industry, uses holding ponds to recapture their irrigation leachate. So this is one way to introduce cleaning it up with biological controls that take no energy once you installed it. Not quite as effective as the constructed wetland, but you can see you can reduce nitrogen and phosphorus nearly by half. Next slide. Okay, I'm all done. Let's look at the results of our poll. Looks like a lot of you have downloaded one. Thank you from the bottom of our hearts. We appreciate that. Next slide. Next, we're going to have Caleb step up and talk to you about incentives. No polls on this. We're just going to jump right in. Caleb, the microphone is yours.
Thanks, Rob. Hi, everyone. My name is Caleb. I'm a program manager working for ICF. I manage the two agricultural energy efficiency programs that we offer to customers in Southern California. ICF is the main implementer for the program. And also working on the program is NSAVE. I'll have a slide at the end that has contact information for both of us. Feel free to reach out to us with any questions. So first, I'm going to go over some of the electrical measures that we have on the program. The list you see in front of you is for deemed measures. These are measures that require equipment to be new, already installed within this year. And it's a prescriptive rate, so we're paying based on the unit or based on the unit's horsepower. So we have everything from glycol pump VFDs to ventilation fan VFDs, irrigation well VFDs. We do have high bay LED lighting that we can offer. Right now, it's not for plant areas. It's only for head houses, hallways, storage, or office space. But ICF is actually working on a statewide work paper to be able to also include plant lighting as a deemed measure. Next slide, please, Bryce. So moving on, some of the custom measures that we offer and custom and NMEC measures are able to be applied to more types of equipment. But the data and documentation requirements are much more rigorous compared to deemed measures. But again, we're able to work with more equipment, possibly. So we have various different lighting measures, from lighting controls to, again, interior high-low bay LED lighting, custom HVAC measures, and then also refrigeration measures. We can offer incentives for post-harvest processing as long as the processing is co-located within the farm that the crops are grown. And you can see the incentive that we offer is 15 cents per kilowatt hour plus 150 per kilowatt in savings for custom electrical measures. Next slide, please. Some more custom NMAC measures that we have on the electrical side include irrigation, compressed air, pumping, and wastewater measures. Same incentive rate of 15 cents per kilowatt hour, and then $150 per kilowatt. Next slide, please. So moving into some of the gas measures that we offer, what you see are, again, deemed measures. The gas measures are split out by 3 incentive levels. There's the standard rebate, an increased rebate for DAC customers, which is based off of a statewide classification of different areas. You can find the actual map for this if you Google Cal EnviroScreen 4.0. And then lastly, we have HTR, which is based on a couple of different factors, mostly employees predominantly being non-English speaking, leasing a building, or having less than 10 employees. So we offer a various amount of measures, boiler measures, storage water heater measures, and those again are paid based off of a unit, whether it's square footage or BTU hours. Next slide, please. Here's some further deemed measures that we offer, again, on the gas side. They also have the 3 tiers of rebates. Additionally, we have tank insulation, fitting insulation, and pipe insulation. Some of these measures you'll see in the far right column. If you qualify as HTR, we can actually offer them at no cost, where we're sending in a contractor and having them do all the work without any payment out of your pocket. Next slide, please. Then lastly, in terms of deemed measures for the gas program, these are our largest measures that we work with. They include greenhouse heat curtains and greenhouse infrared film, both for existing structures or new construction. Again, these have 3 levels of tiers for rebates: standard, DAC, then HTR. And again, the heat curtain and infrared film measures, if you qualify as an HTR customer, we can offer at no cost. Next slide, please. Finishing up, some of the custom measures that we provide for the gas program include boiler system upgrades, greenhouse environmental controls, heat recovery, ozone cleaning, and then greenhouse retro commissioning. These are also tiered, but there's only 2 tiers. There's the standard incentive, and then a DAC and HTR combined incentive. And then you'll notice for greenhouse retro commissioning, the incentive is about half of the other measures. Next slide, please. Some of the basic eligibility requirements. The customer must meet the program eligibility requirements. This includes being a customer for either SoCalGas or SoCal Edison. All equipment must be new, either electric or gas powered equipment. The qualifying equipment must be purchased and installed either within this calendar year or within a calendar year of its purchase date. It's a little confusing, so if you have any questions about this, again, feel free to reach out to us and we can clarify. And then lastly, all efficiencies have to exceed Title 2024 standards. Next slide, please. Some of the program delivery services that we offer include training and education, both energy savings and non-energy benefits, building energy assessments, energy benchmarking, technical support, ongoing guidance in terms of what measures you should be working with and when you should have them installed, possible financial assistance through grants or on-bill financing. And then lastly, we do dedicated outreach for DAC and HTR customers. So in general, we're willing to help you through the entire process if you're willing to reach out to us. Next slide, please. So this is my contact info up top, and then there's also Ben Cooper. We're both program managers. Feel free to reach out to us with any questions and we'll point you in the right direction. And thanks, Rob, for having me.
You bet, Caleb. That was wonderful. So great services you provide. And then some of these incentives, I just want to point out, actually impact water conservation too. For example, they give an incentive for infrared films, infrared inhibiting films, which are for greenhouses. It's a film. Typically, they're a flexible film like on a polyhouse, but now they're beginning to be produced as a rigid panel that allows light in, but not the heat. So you have a less cooling demand, right? So that means that your cooling pads for your greenhouse don't have to operate as much. So you're not going to be consuming so much water. It also means your plants aren't going to be drying out so much because you're having another way to control heat buildup. And so the irrigation would be reduced. So always keep that in mind. Some of these great technologies can be used for water conservation. Actually, some of the questions that we have are meant for you, Caleb. So I'm gonna, if you can turn your microphone back on. Evan has asked, what about post-harvest processing rebates? Is there anything about the post-harvest aspect of cultivation that you can?
Yeah, so we can offer incentives for post-harvest processing. Again, the processing has to be co-located on the farm. There's a various amount of measures that we can offer. Bryce, if you want to go back maybe to like the very first slide. Some of the deemed electrical measures. One of them is dust collection fans, which can be in different types of post-harvest processing. Custom measures, there's a long list. Refrigeration or anything HVAC related, even down to the lighting in the post-harvesting areas. If it's high bay lighting, we can provide an incentive for it. Could you go to maybe like 2 more slides, Bryce? So there's steam traps that we offer, water heaters, boilers themselves. That's included in post-harvest processing. Next slide. Any insulation. Next slide. Probably not heat curtains or infrared film, so next slide. Right. Boiler system upgrades, contact water heaters, infrared heating for post-harvest. So I've seen that in a lot of nut processing of post-harvest. Process heat recovery. Yeah, there's a lot. So the best answer is just to reach out to me and I can clarify what would specifically apply to the operation you're running.
Wonderful. That's a great answer. By any chance, I was looking down the list. Is there any sort of incentives for upgrading your environmental control system to something that would do a better job of tracking energy use, water use, and also just being more, helping the operation be more efficient?
Yeah, and we can do indoor. It would have to be run as a custom project.
Yeah,
and keep in mind.
I'm sorry, it was right on your list and I was blind. 4 down on the slide, greenhouse environmental controls.
Yeah, and it has a lot of documentation requirements. So expect that, and it's not a quick process. It can take 6 months to over a year. We'd like to have a deemed rebate for greenhouse controls, but it's such a complex thing to manage energy savings on that it's probably not happening anytime soon.
Yeah, well, great answer. Appreciate that so much. Well, our time is up today. I hope we've answered most of your questions. You've been a great audience. Thanks for sticking with us. I'd like to thank Jeff Martens and Caleb Hayhoe and Carlos Salazar for being a fantastic part of our presentation today. For Bryce Carlton, I'm Rob Eddy with Resource Innovation Institute. Thank you for your attendance.